integration techniques are really about pattern recognition. So part of what we're trying to do is see a bunch of different kinds of integrals, see how they work out, and get some experience with those different kinds of integrals. And eventually, you'll begin to see patterns. You'll be able to understand with a little, almost intuitively, when to apply a certain technique, or when a certain technique is going to be not useful. The integration tables, the formulas in the integration tables, all come from techniques that we've already learned. Integration by parts, trig substitution, partial fractions, hyperbolic functions. There are some more advanced integration techniques, but all the tables have been developed from techniques that we already know. The nice thing about using tables is if you get to an integral that you don't know how to evaluate, you look it up in the table, you see the form of the answer, and sometimes that suggests, oh, this is how I evaluate that integral. You see the form and you say, this looks like they did something, and then they ended up integrating this particular quantity. So integration tables can help you, even if you're not looking at the integration table to get the answer, you can look at the integration table and it can suggest a path that you need to take to evaluate a certain integral. So that's why I think that integrating by tables is still a useful technique. And even if you have some computer program like Mathematica or some other program that will evaluate integrals symbolically, you can see the answer and say, oh, I think that in order to get an answer that looks like that, this was a partial fractions, or this was a trig substitution, and you end up integrating the integral of secant theta d theta, and that's how you come up with this answer. So that's why I think that that is still a valuable technique. A lot of the integrals that in the tables that you get to, evaluating them are extremely algebraically intense to evaluate the integrals. So sometimes we can look to the tables to minimize our work. In your book, our book has evaluation or integration tables in Appendix B, which is on page A20. And there's a pretty, a decent integration set of integrals in that appendix. So if you're ever working on homework and you get to an integral where you really just have no idea how to evaluate it, you might try looking in that table and looking up your integral in there. Now the challenging thing about the integration tables is that sometimes we need to work with the particular integral that we have to get it into a form that lets us use the integration table. So I just want to look at, I'm just going to do one quick example. Let me pick a good one here. All right, so let's look at, I just want to do an example of using the integration table. So let's say we have the integral of dx over x times the square root of x minus 1. It looks kind of not nice. This square root of x minus 1 suggests maybe a trig substitution. If I maybe let u equal the square root of x, so then this would be u squared minus 1, and this would be u out here. That might be a trig sub integral. But if we saw this integral and we were stumped, so I'm going to look in the table, and I'm looking for, you notice in your table it has different forms. It gives you the forms involving such and such, forms involving various things. So if we look at, I'm looking at formula number 17. Formula number 17 is exactly the form of our integral. If I look at formula 17 in our book, in our integration table, it tells us that the integral of du over u times the square root of a plus bu, and here a is less than 0 for formula number 17, is we're picking the form where a is less than 0. In our integral, a is negative 1. So it tells us that this is 2 over the square root of negative a times the inverse tangent of the square root of a plus bu over negative a plus c. So if we looked at this in the table and we saw this inverse tangent, that would be a hint to me that yes, this probably is a trig substitution integral. But if we didn't want to go through the trig substitution, or we didn't have to, we can plug our numbers into this formula. In our integral, we have a equals negative 1, b equals 1, and u equals x. We also need to transform our dx. du equals dx. So just like when we do trig sub, we have to take into account our dx. Sometimes that comes into play. This should be du. So du equals dx. So I'm just going to plug this in here. So our integral, the integral of dx over x squared x minus 1 is going to be 2 times the inverse tangent of square root of x minus 1 plus c. If a is negative, so since a is negative 1,
they're two different.
Right. So if you look at in your table in your book, I'm on page 821. It gives a different case if a is positive. It gives a different case if a is positive. So this is a little easier than going through the trig substitution. If you're not required to do the trig substitution, this would be an easier route. And I remember once when I was in college, I was taking a class called Mathematical Methods for Physicists and Engineers. And it was all about different techniques that you use in your different classes. And I really liked doing integrals. I liked figuring them out. I liked trying to figure out if I could do the trig substitution or the partial fractions or whatever. And I was working on this integral, and the instructor came over and he said, "What are you doing? Look that integral up. Like you don't actually do the integral. You look it up in the table. You're crazy for doing it." So if you're in a situation where you're not required to demonstrate that you know the technique, or that you just don't want to, then tables can be a valuable resource. Let's see. Let's look at one more where we have to deal with a transformation for our dx. So just one more example using our table. Any questions on what we did there before? I'm thinking that I'm probably not going to put a integral where you have to look it up in the table on the test. But it is a good technique and that Chris mentioned it the other day, and Liam mentioned it today. You get to an integral where you don't know how to evaluate it, look it up in the table. And you might find it in the table, and that also might set you on the track for how you need to evaluate the integral. So let's look at the integral of x over 1 minus e to the minus x squared dx.
Negative x squared.
Yeah, negative x squared, e to the minus x squared. So this looks like it could be a u substitution with u equals minus x squared. It could be. So it doesn't necessarily look like a nice integral. So I'm going to look for, in my tables, I'm going to look for forms with e to the u. So I'm looking through my tables here. So I think 84 is very similar. So let's use number 84. So we're using number 84. And I'm going to say that, and in formula number 84 says that the integral of du over 1 plus e to the u equals u minus the natural log of 1 plus e to the u plus c. So let's let u to make the form of our integral match the form of this, let's let u equal minus x squared, and then du is going to be minus 2x dx. So we have to take into account our du. The du for our substitution, so du is minus 2x dx. So we have this factor of minus 2 that we have to deal with. We don't have it in our integral, so we have minus 1/2 to account for that minus 2. The integral of, and I'm going to make my substitution minus 2x dx, that's my du, over 1 plus e to the minus x squared. The minus 2x dx is my du, and 1 plus e to the minus x squared is 1 plus e to the u. Oh, did I miswrite my... Oh. Sorry, this should be a plus here. I miswrote my problem initially. So here's my du, here's my 1 plus e to the u, and this factor of minus 1/2 takes into account that we don't have this minus 2 in our original integral. And I just plug into my formula, so I get minus 1/2 minus x squared minus the natural log of 1 plus e to the minus x squared plus c.
Can you bring up the negative 1/2 in front? That doesn't, normally when we do that, then it would be like negative 1/2 du equals x dx. Can you leave the two at
I just left this in to remind us that this whole thing is du.
Oh, okay.
And this whole thing is 1 plus e to the u. So this is my du, this whole quantity in the numerator, and 1 plus e to the minus x squared is 1 plus e to the u in the denominator. And we don't have this minus 2 in our original, so I'm dividing it by minus 1. Does that make more sense?
Yeah.
Okay. I just substituted in a little more than maybe normal. All right, so those are a couple of examples of how you might use your integration tables. As if you looked at the book that I passed around, there are a huge number of integrals in that table. So it's good to have available a lot of techniques that you can fall back on to evaluate integrals. And understanding different types of integration techniques allows us lets us be familiar with different forms and maybe predict how the answer might look. Or from looking at the tables, like I said, if you look to see how the answer looks, you might have an idea of what technique you have to use to evaluate your integral. All right, questions? Homework. I think you'll find this one a little easier than the last one. There you go.